Embarrassing correction. This is butthead. This is not Beavis. Okay, yeah, sorry. I can't believe. So
it's tragic that no one corrected you.
Exactly. It's tragic.
We're all
too old. Exactly. Right. Yeah.
Somebody corrected him.
Yeah, somebody is.
Sorry.
It's good.
It's good.
Because it was so embarrassing, he corrected me in private. So, butthead, yes, right.
Pardon? This is not Beavis, it's Butthead.
The most famous quote is Seattle like in America? All right. Lenora.
Before you go ahead, I'd like to make a comment, okay? The real definition of NP could be stated in a little different way, saying that they're problems that are easy to check or easy to prove once you have the proof. They're exponential, we know now, but they're not all, it's not equivalent to exponential. And I think philosophically, that is a really good way of thinking about it as contrasting easy to find and easy to prove. They're two different notions. Easy to find a proof, easy to prove something. It's very hard often to find a proof. It's often very easy to check a proof.
Yeah.
And I think
Thanks, Lenora.
the PNP question said that way is philosophically very interesting. I think that actually is, from computer scientists, was really an intellectual understanding of the difference. So
I agree, yes. So thanks for your comment, Lenora. Obviously, I work on this. I sort of, there are the 17 different ways of explaining things, and for this audience, I had made the choice. Or you think it's the wrong? You're probably right. So, excellent. Let's go ahead with the Perceptron algorithm, and that's sort of a familiar concept, obviously, right? I mean, so it's what you are given. So basically, going beyond online problems where you don't have an input, but but you are facing a prior free situation every time. What happens, is that you want to learn a distribution. Okay, you want to learn some kind of points distribution, and the sad fact is that we know how to do it. One thing, and that's learn planes, okay, hyperplanes. That we know how to do well, and so and I'm going to present this because it's an extremely simple algorithm. So you are given, you are promised that I'm going to give you a set of examples, okay, and they all come from all the positive examples come from one half of the space. And all the negative examples come from another half of the space. Okay, that's the promise. All right, and let's say the hyperplane goes through zero, and everything, all of this, can be reduced to this simple case. We know that the pluses and the minuses are separated by hyperplane. So you can think of it as the vector is the characteristics of emails. And the plus or minus, is it spam? Is it not spam? Okay, something like that. This problem is easy because you are told that there is a hyperplane that defines it, okay? So, real problems are not like that, okay? But let's solve this problem and see what you can do. And in fact, there is some positive number m which gives you a margin, okay? In other words, if you tweak the hyperplane a little, okay, it's still going to be good. It's still going to separate, okay? There is a margin, all right? So that's what we are given. And I'm going to show you how to solve this. And because the algorithm is extremely simple. You are looking for this hyperplane. You start with a bad guess, and you update it for its example. If you make you have a false positive, you add it. If you have a false negative, you subtract it from W. Okay? And the theorem says that if a hyperplane exists, it will be found after at most 1 over the margin squared mistakes. Okay? So this is the theorem. It has a very simple proof. It sort of it solves a problem. It solves an embarrassingly easy problem, right? Because in real life, but the reason why I'm bothering you with this is because it's the beginning of a glorious story, right? So we have known this since the 50s, 60s, of course, we know that usually pluses and minuses are not separated by hyperplanes, right? So what do you do with this? And there is a beautiful trick that you can use here, and I'm going to do something that requires courage, so please bear with me, because I'm going to show you a video. Okay, I don't have it. Okay. So I guess I'm going to search for. Oh, it is?
No, the first tab.
Is it? Thank you. Okay. So the way I found it, because I'm sure that you will want to play it again, I typed on Google kernel trick YouTube. Okay. Here's what it gets you, okay? These are some blue points separated from the red points by a circle, right? Like the ones I showed you. And obviously there is no hyperplane but then if you add this third dimension, okay, chosen carefully, look what happens. The blue points and the red points can be separated, okay? Because the third dimension helps, okay? That's the point. And this is what makes this is what makes this Perceptron algorithm valuable, because it can be enhanced by these functions. Okay, these functions have to be in some sense positive definite. Okay, and in a very well defined analytical way. And so the way that it became sort of a very interesting idea, very interesting industry. It's called support vector machines. And the idea is that if you have a data set that looks very difficult, if you stop and think, and you come up with a bunch of interesting functions that you can add to the dimensionality of the problem. If you are lucky, and or if you have the magic, okay, so because this is also an art to find the right functions, then you are going to get the Perceptron algorithm suddenly is going to work, okay, so and with the same complexity as the simple Perceptron algorithm, all right. So this is sort of a very interesting fact. And the support vector machines were a huge thing, a huge wave of success for artificial intelligence, until of course they were dwarfed, by who? Deep nets came around, okay. There were there was a glorious history of success, the last half decade or so, all right. Of more and more amazing problems solved by deep nets, including vision, including speech, all right. So just to touch on what is the kind of problems that we can attack by deep nets, I'm going to tell you a few things about sort of the other, the more general form of supervised learning. Okay, so and the question is, imagine that we want to answer the question, to classify apples into tasty and non-tasty. Okay, And as we know, this depends on the color of the apple and on the diameter of the apple, all right? I mean, so, and let's assume it does, all right? I mean, that this is enough to determine, all right? I mean, so, so let's see, what is this problem? I mean, how do you define this problem mathematically? Essentially, you are given a distribution, all right? I mean, these apples are good, these apples are not so good, right? I mean, so you are given a distribution. You are given a distribution of labeled examples, right? I mean, that this is sort of more likely to be in this elongated ellipse para than the others, and then you are given, you are looking for labeled examples. There is some hypothetical function that maps points on the plane to good or bad, sampled from this distribution. Basically what you want now is you have a class of learning hypothesis, okay? You have an idea of what is the shape of good apples, okay? And imagine that you think that the shape of good apples is a rectangle, right? I mean, so you are looking for, your space of hypothesis is the space of all the rectangles, and you are looking for the best rectangle to fit your data, okay? This is the kind of problem that I want to discuss next, so very briefly. And is it clear? So I want everybody to understand. So you have a distribution from which you get good and bad apples labeled. That's why it's called supervised, right? I mean, because nature helps you. So every time you are in doubt, you can say, let's go to the supermarket and get another apple. You have a class of learning hypothesis. In other words, what is your goal? What is the shape of your that you are seeking of understanding what it means to be a good apple, okay? The goal is what is called in learning theory probably approximately correct. So it's a beautiful phrase tossed by Les Valiant, in the 1980s. Basically, what we want to do is we want to select one of the hypothesis H, such that probably to 1 minus delta, some small delta, it's approximately correct. Okay? So you want to find the hypothesis, which is probably approximately correct. An important question that comes to mind, okay, that classifies essentially these problems to harder and easier, is this box hypothesis, this rectangle hypothesis. Do you know that your good apples are in the box and the bad apples are outside the box? Or this is sort of, you have to restrict your state of hypothesis and that's how you did, okay? And of course, the second case, where you are not sure that the good apples are in a box, okay, is much harder, right?
What is the domain of the first probability?
Excuse me?
What is the domain of the first probability? Because 1 minus epsilon and 1 minus delta both are probability. So,
the domain of the first probability is basically the randomization in your algorithm.
No, it's the randomization of picking examples.
Exactly, it's a randomization. You are going to run a randomized algorithm here.
No, anyway.
Sorry, please. Yeah. So you are going to run a randomized algorithm, and you want to it's a randomization of your algorithm. Okay. Shai wrote the book on this. Okay, so I'm rewriting it right now. Okay. Okay. All right. So, and here is the algorithm. Draw from this distribution a sample of labeled points of the form x plus or minus. Very simple. Find the hypothesis H in your class of hypotheses that minimizes the number of misclassified points S. Okay? And that's it. What I have to do is to tell you how big is S, because that's the only thing I want to tell you, right? I mean, because otherwise we're going to draw it by chance, right? and how to solve this problem. Okay? And these are, of course, are the $60,000 questions. Okay? How hard it is to solve this problem, is the hardest of the two. Okay? So I'm not going to talk about it. Often this problem is NP-complete. Often it's NP-complete, but can be solved by backpropagation, okay, by gradient descent, empirically very well. Okay. So I'm not going to address this. It's a deep question, but I'll show you the theorems you have about the size of S. Okay, what S is. Again, my goal here is to give you a very, very short sort of smattering of results we have in learning theory. Here are the theorems we have. I realize learning theorems is ambiguous. I mean theorems about learning, okay? Yeah. Okay, so I'm not requiring you to learn these theorems, right? So under the realizability assumption, that many samples suffice, okay? So if you know that your apples are in boxes, okay, and you have a set of boxes to try, then, and you know that in one of these boxes is the right answer, then you need to have that many, you know, in other words, you see it's a decreasing function of epsilon and delta both, and an increasing function of the size of H. Without realizability, roughly speaking, we need more samples, essentially by a factor of 1 over epsilon. Okay, so you need many more examples, because epsilon has to be like 1%. So you need maybe thousands times more examples. And the logarithm of the size H can be replaced in the above by a fascinating set theoretic concept called the Vapnik-Chervonenkis dimension, okay, the VC dimension, okay, which essentially says how sophisticated is your H, okay? If I give you k points, will you be able, and I give you some partition, I want this to be plus, this to be minus. Will you be able to find an H that does this, okay? And can you do it for any set of k points? Okay. Then your VC dimension is bigger than k. All right, so this is my sort of very quick. There are many beautiful books on learning. The more theoretical one that I know is a very early one by Kearns and Vazirani. And Shai's book is an amazing book. So, you know, it's called Understanding Learning Theory. How do you call it? What's the title?
Understanding Machine Learning.
Machine Learning, yes, Understanding Machine Learning. So, I didn't have it in front of me. I have it in Colombia when I prepared this talk, but I tried to recall it. Okay, so great, excellent. So now I'm going to tell you about a fascinating subject, which is computation as a lesson of the sciences. So what I want to tell you, what I want to convince you, is that engagement with neuroscience is not our first bout. Okay. We have a long history of engaging with other sciences. Okay, you know, and I'm going to show you sort of, you know, what does it mean, the computational lesson of the sciences? Okay, remember the first slide about computer science that I showed you. Okay, sort of the epic of studying the computer and solving the engineering problems associated with the computer. So this experience has transformed my field. Okay, so, you know, basically, we developed a very special way of thinking that is, of course, mathematical in some sense. It's also practical in other cases, but definitely it has sort of, you know, we call it the algorithmic way of thinking, the computational way of thinking. Okay, and it's this very distinctive, all right. I mean, so if you watch us talk to one another, so, you know, you'll see that we speak sort of, you know, in a particular tongue. Okay, you know, that we call the computational way of understanding the world. And the point is that this is a new way of understanding the world, and so occasionally, I'm not saying often, I'm not saying most of the time, you know, but occasionally, if we look at a problem, at a hard problem in another science, we have a new idea. Okay, that's my point. All right, I mean, and let me show you a few examples. Okay, the first historical example is this, or you know, is statistical physics, right? I mean, so and the pioneer in this is the former associate director of the Simons Institute, Alistair Sinclair, my former colleague at computer science at Berkeley, and basically, you know. As you know, as most of you know, one of the central problems in statistical physics is the problem of phase transitions. Okay, how does a lake freeze? How does a change in a parameter completely change the nature of the interactions of a large population of particles, local interactions, in a way that is qualitative? Okay, so and suddenly, so you know, the lake freezes. All right, and in 1989, it was sort of observed that phase transitions are tantamount, coterminous, equivalent. In other words, what phase transitions really mean is that one particular randomized algorithm converges exponentially faster. Okay? And this was sort of, you know, an incredible insight that changed the field dramatically, in the following sense. I mean, that's in some sense the greatest success story. That now there is a new field in which physicists and computer scientists work together. Okay, and you have great algorithms published by physicists. Okay, sort of, you know, and theorems in physics proved by computer scientists. Okay, you know, you have this very active and harmonious sort of reaction, interaction between these two fields that is going strong now. And has really changed the discourse in statistical mechanics. Another famous example. In 1982, Richard Feynman wrote an amazing paper called Simulating Physics by Computers. Okay, so as I told you, I teach this class reading the classical papers in computer science, and I consider this one of the great classics of computer science, okay? Because this man said it better than any computer science has, what it entails to simulate physics by computers, okay? And then he noticed that there are some systems, namely quantum systems, which need exponentially many parameters to be described, okay? And I mean, there are two ways to react, right? I mean, one is to be a conscientious computer scientist and panic, okay? So, you know, say, you know, what am I going to do here? Or be Richard Feynman and turn the question on its head. And then say, okay, these are tough systems, but what if we build a computer out of this? Okay? And the point is that the ensuing 10 years, work by physicists and most remarkably computer scientists like Umesh Vazirani, my colleague here, and Andy Yao, they created sort of, they created the Turing machine for quantum computation. So, you know, the canonical example of quantum computation, and I mean, the rest is history. And a huge part of this history is the fact that the intractable problem that I mentioned before, okay, that you cannot factor integers, can be solved in polynomial time by quantum machines, okay? All you have to do is input the 1000-bit number here, 1000 bits, that's 300 digits. That's 10 lines, okay, so you know, it's on your screen, right? I mean, it's a lot. You create you create slowly from this number a superposition of 2 to the n states, 2 to the 1000 states. You maintain this superposition and you manipulate it. And after maybe not 1000 but 1000 cubed steps, you measure it, okay? And the measurement with high probability is the factorization of the number, if it exists. Okay, so this is sort of an amazing result due to Shor that sort of, made everybody pay attention to quantum computers. I like this quote because it tells us that's not the point, okay? That's not the, factoring is not the point. Building powerful computers is not the point. What the point of quantum computation is testing quantum theory, okay? Seeing if, to what extent it generalizes to many, generalizes well to many particles, okay? And this, of course, as you know, is an ongoing research endeavor that is sort of, it essentially it takes through hoops the most prestigious theory of the universe, and the hoops are computational. Okay, that's essentially the idea. All right. So we talked about statistical physics. We talked about, I'm running out of physics fields, so let's go to social sciences, and then life. Equilibria, all right? What is equilibria? Equilibria basically are predictions in economics, all right? Economists think that when a population of agents interact in an interesting way, eventually they reach an equilibrium, and this is our prediction, right? This is how we predict it. And famously, John von Neumann in 1928 proved that games have an equilibrium as long as they are two-player and zero-sum. In other words, almost never. Okay, and it took another 20-something years for Nash to prove that all games have one. Okay, and this is the moment of birth of modern game theory. Okay, so that basically the proof of Nash is sort of made game theory to a science, right? Not only that, it's in some sense started all of modern economics. Here is why. Because two clever mathematicians, Kenneth Arrow and Arrow and Debreu, a couple of years later, were inspired by Nash's proof and proved their welfare theorems, right? That all markets under assumptions have price equilibria, okay? There are prices that can clear all well-behaved markets. Because of this, Roger Myerson wrote a few years ago that the Nash equilibrium lies at the foundations of modern economic thought. What he meant by that was this incident, but also, more importantly, the fact that the Nash equilibrium is a license to any economist when they're thinking about a market or an institution they're designing, or any situation in which agents interact in interesting ways, to say, okay, let's see what happens at equilibrium. All right? So, by the way, this slide has 20 words or less, and has 4 Nobel Prizes. Okay, it's not easy to do. Okay. Okay. And the surprise is that the Nash equilibrium is an intractable problem, right? So we had a very nice dialogue before, right? That what does intractability mean in practice? Okay, and I'm all with you. Okay, I totally agree that in practice, intractability may not mean much. Okay, but in theory, okay. And what I said before, okay, what Myerson said, is that the Nash equilibrium is a theoretical problem. It's a theoretical tool, okay? In other words, what I'm saying is that the intractability result says that Nash's theorem is equivalent to saying that almost all games have a Nash equilibrium, okay? And believe me, if Nash's theorem said that, the world of economics would be completely different today. Okay? It's important that all games have a Nash equilibrium. It's theoretically important that all games have a Nash equilibrium. Okay? To put it in the wise words of my colleague Kamal Jain, if your laptop can't find it, neither can the market. Every time I show this quote to economists, I get into trouble, I get into a long discussion, at the end of which we agree, okay, the market is not a laptop, but it's a bunch of laptops, you know, but it's the same thing. All right. Good. Let's go to finally to life sciences, all right? I mean, and I'll tell you just 2 words about some work that we did on evolution. So, you know, Jacques Monod said that evolution is funny because it's, you know, in some sense among all scientific fields, has the highest ratio of people who think they understand something about it versus those who actually do, okay? And frankly, in a bad day, this ratio looks infinite, okay? For example, I don't know if you are aware, but 150 years after this 160 years now, after this wonderful book, we don't know what is the role of sex, okay? I know all of you have heard the theory, and that's your favorite theory. Experts agree that none of them explains why sex is so predominant. While they look around, you are all different. I mean, if selection is the point, why are we all different? Why haven't we converged to some great phenotype? Is evolution optimizing something? Okay, that's sort of a theoretical question, but it has been torturing evolutionary theories since the inception of mathematical evolution, or since the days of Fisher, Wright, and Haldane. Okay, Fisher had an idea. You know, Sam Carlin famously worked on finding the Lyapunov function for evolution, but we don't know. Okay, so let me show you a result. Okay, no, before. Here is how a theoretician, theoretical computer scientist would ask the question. What algorithm could have done all this, okay? All this in a mere trillion steps. Why trillion? Trillion is the number of generations since the dawn of life, okay? And trillion steps may sound a lot of steps, but your cell phone has done a trillion steps since the beginning of my talk, okay? And it hasn't accomplished much, okay?
Well, that number of organisms is also growing.
Excellent, okay, so he's asking a great question. I'm not going to get into it. Is this the right thing? Or is this times the right number of species? Or this times the number of organisms, or this times the number of cells in these organisms. Okay, what is the real laboratory? Okay, and I am one of those people who believe that the laboratory is a generation. Okay, and I'll show you why. I mean, I'll show you why I think so. Okay, good. So let me. I know. So you know. So this is where I'm starting to cash on my equation credit. Okay, so you know, I know I shouldn't put too many equations. Okay, but here is one I want you to see. This is very simplified case. We can do it in more complicated cases. But suppose that you have evolution of a haploid population. We are diploid. In the weak selection regime, this means that that selection is not dramatic. Okay, so selection forces are not dramatic. They are like smooth. Okay, and this is something that evolutionary biologists have no trouble admitting. And we have the gene who just, you know, we are focusing on 2 alleles with 1 gene and 2 of its alleles. Okay, and now consider what are these numbers? This is the frequency of allele 1 at generation t plus 1, I guess. Okay, so the allele 2 is 1 minus xt, okay? All right? And basically, I'm telling you how this quantity goes from one generation to the next, okay? And this equation, we wrote it for the first time, okay? But it was really, I mean, there are thick volumes with mathematics on evolution, right? And this equation was 3 algebraic manipulations away from equations that were already there, okay? But once you see it, you know, once we saw it, sorry, my voice is breaking. So, you know, I heard Umesh, you know, my co-author, say, now I have faith in evolution. You see why?
What is S and F?
Okay. So what I'm saying, so the question is, basically it says the following, that the frequency of allele, of the first allele, is, okay, sorry, yes, so, you want to see this?
Yeah, what are S, F, and
I'll tell you.
It's the same.
The sum of all the x.
Yeah, okay. S is the selection strength, sorry. And we're assuming that it's very small, okay, because we're in the weak selection regime. You know what 1 is? XT is in the previous generation, right? And what is F? F is the relative fitness of allele in the present genetic environment. I'm saying the following, that the organism has an environment around it, and its fitness it depends on it. But also this gene has also a genetic environment around it. The other genes that it interacts with, okay? And they create another fitness, the relative fitness, which is this one, okay?
So all the fitnesses sum to 0 or something like that?
Not necessarily, because you can, you know, they will sum to 0 eventually because you are dividing by this, all right?
Okay.
If you wish, yeah. Some, you know, okay? Okay, so that's the equation, and I mean, we derived it, but it's like a really high school job to derive it.
What do you mean derive? It's like, it's just intuition, it feels like.
It's very intuitive, sort of, you know, and you can get it out of the math that people had. Okay, there is sort of a very complex theory, sort of, you know, of page-long equations, you know, and if you specialize to this regime, okay, you get this equation. That's what I'm saying. And if you look at this equation, sort of, you know, my jaw drops. You know why? Because this is multiplicative update. This is the multiplicative weights algorithm. Okay? So it turns out, okay, that evolution uses multiplicative weights, okay? Sort of, there is much more. If you ask yourself now the following question, okay? So every generation, this gene has to select xt plus 1, okay? And selects it this way. Why? What is it optimizing by selecting it this way, okay? And here is what is optimizing. Okay? This is the potential function, the Lyapunov function that this gene is optimizing, okay? And it has 2 terms. One term is sort of, you know, the sum over all previous generations of the differential fitness of the first gene from the second gene, the differential relative fitness. And the second one is a huge factor times the entropy of the distribution. Okay? All right, so, I mean, let me explain why I find this, you know, first of all, it is an explicit function which genes seem to be optimizing, okay? And this is interesting. Number 2, it has a fitness term, and then it has an entropy term. This means that the genes, when optimizing the reaction to the genetic environment, they are mindful of diversity. Okay? They don't want to go all in. Right? I mean, they give a lot of weight to the entropy of the distribution. Okay? So, nothing more. Just want to remind you the 4 questions I asked. What algorithm could have done this in a mere trillion steps? I think now I know.
You should maybe tell people what is entropy.
Entropy is sort of is Shannon's measure of diversity. Okay, it's the sum of the logarithm of inverse probability. That is, is the expected inverse logarithm of the inverse probability, and it's basically it's maximum when it's 50-50, and it's sort of the standard measure of diversity. And so, what is the role of sex? My biology co-authors don't like me to say that, but I'm convinced that the role of sex is to enable the multiplicative weights algorithm. Okay. Why all this diversity? Well, I don't know, but genes seem to be mindful of diversity. Is evolution optimizing something? I don't know either, but I think that I know what genes are optimizing.
Excuse me, can you go back to the equation?
Sure.
So is there a competition between those two terms?
Yes. Yes, very much. Because basically, this wants to keep it close to half,
Yeah.
and this wants to keep it to at either 0 or 1. So whatever is the sign of this, of this sum,
Oh, I see.
right?
That sign is fixed.
Yeah. Okay. There's a competition. There is a clear competition of the logarithms.
And there's no another parameter lambda that's like a temperature there?
Well, the temperature is this, okay? Because the more time goes on, this term will become bigger, and it's going.
Temperature in physics is usually on the entropy side.
I understand, but here it's okay.
You can actually prove that this.
Yeah. Yes. Yeah. I mean, prove it. A freshman can prove it. Yeah, you just Kuhn-Tucker, yeah. Okay. Okay, good. And now I'm going to tell you about TCS and the brain in the last 15 minutes as promised. So I'm going to talk a little bit about my work, and it's not because Wolfgang talked a little about it yesterday. It's not because I think you should know about it, but because I think it's it's an interesting specimen of the form. How would a computer scientist first start working on the brain? All right. So all right. So this is what we are all interested in. Okay. In fact, I like to call it a sunset from the Berkeley Hills question. All right. I'll call this question. Here's what I mean. That every time I see this view, what comes to my mind is, why doesn't everybody stop what they're doing and come here to watch this? Yeah. So when I think about the brain, I'm in the same mood. Okay, why are people working on something else? And given my background, and because I want to believe that the answer, once we find it, it's going to be at least partially computational. I want to answer this question. How does one think computationally about the brain? And the point is that good people have worked on this, or have thought about this. Turing have been thinking about the mind all his life. Okay, so von Neumann, towards the end of his life, wrote an amazing book, which I highly recommend. I read it after Wolfgang recommended it to me, and it's eye-opening. Okay, so it's eye-opening how somebody, in 1950, could have this insight about the brain. So here is one insight. The way the brain works may be characterized by less logical and arithmetical depth that we are normally used to. Okay, so if you are if you are hoping to find your favorite sophisticated algorithm in the brain, so remember von Neumann, right? I think he's right on the spot. Les Valiant, professor at Harvard, the founder of learning theory, he worked in the 1990s on the brain, and came up with a very interesting model, came up with a well-developed theory, wrote a book, Circuits of the Mind. But here I'm going to quote a beautiful sentence of his, that a computational theory of the brain is both possible and essential. Okay, so and he elsewhere says that one of the founders of sort of, of brain theory, of neuroscience, would be surprised that there are not many competing theories of the computational theories of the brain right now. Okay. Okay. And of course, David Marr. A lot of people talked about him. I mean, the way I transliterate his program in modern computer diction is that he wants us to think about specs, by which I mean the input-output behavior we know the system has. Hardware, what are the physical elements that are implicated, and the algorithm. What are the processes whereby these physical elements are put together to achieve these specifications. And let's remember von Neumann that we should expect this algorithm to vanish often. Okay, so to be so simple that it barely deserves the name algorithm. Okay. Okay. So let's start with the specs. Okay. So I'm going to describe to you something that also Wolfgang mentioned, and I'm going to use sort of a running example that is not accurate in terms of but it captures the essence of what they found. They let's say to keep the story simple, they recorded from a few dozen neurons from a dozen or so patients, but let's focus on one subject and one neuron. And they showed them about a couple of hundred in a very strict regime, a couple of hundred of pictures. And this particular neuron fired every time the Eiffel Tower was shown. Okay, you show other well-known sites, nothing. Every time the Eiffel Tower is shown, it fires. You show him, he used to be our president, remember? Doesn't fire, okay? Then they do the following, okay? They Photoshop Obama in front of the Eiffel Tower, okay? And they probably do it in a more artful way than I did here, okay? And of course the neuron, dutifully, fires because it sees the Eiffel Tower. Then they show the Eiffel Tower, of course it fires. Forbidden City, nothing. Obama?
Fires again.
Fires again. Get it? My voice cracks, right? This guy has learned that Obama has been to the Eiffel Tower, and you discover this experimentally, okay? Okay, so I think I like these specs, okay? So these are the specs, and the question is, what is the hardware and what is the algorithm? And this is joint work with Wolfgang, Robert, both at Graz, and Santos Vempala, Georgia Tech. Let's talk about hardware. So they recorded from a few dozen out of many 10 million euros in the medial temporal lobe in every subject. They showed about 100 pictures of familiar persons in places with repetitions, and they had about 10 hits, okay, which is a lot of hits, okay, because these are many neurons and few pictures, right? So just about the only thing I can explain this is that each memory is represented by an assembly of many neurons. And that's not a new idea. It's an old idea whose time has come. Hebb, of course, mentioned it in 1949, and this is one of the putative ways of understanding how memories are stored. Both Hebb and other researchers, they conjecture that such assemblies are, this is actually a very interesting thing to test experimentally, are highly connected, therefore stable. It is somehow formed by sensory stimuli, probably in response to some attention mechanism. And every time we think of this memory, most of these neurons fire, okay?
It's just a cautionary note that they stick their needle in MTL, which is very close to hippocampus, which does one-shot learning. And they also took the patients and showed them pictures like the test pictures before they ran their final thing. So it's possible that they burned in the picture memory. It wasn't there before they had their test sample.
It wasn't there what? Sorry.
If you just stick the needle there and didn't have the pre-test, you would have seen nothing. But the hippocampus is done one shot. So basically,
right. I mean,
they prepared the patient with a sample of pictures like the ones they were going to test. They created this memory on the fly. It's not like it's not like you could do that from a cold start.
Oh, I see. Okay, it's true that before recording they presented sort of the picture in this regime. I agree. I mean, also it's true that it's close to the hippocampus, but it's not close enough. I mean, they recorded from many areas of MTL that are far from the hippocampus, and I'm not sure where the association neuron. Okay, I understand that. Okay. So I understand that I am also I read the papers. Okay, I'm skeptical of all experiments, right? I mean, but I like this and I want to work on that. Okay, that's my and of course words of caution are valuable.
So you're saying that probably after some, I don't know, a week, a month, you'll do the same experiment with the same people. It will not have the same.
Oh, that's for sure. That's for sure. That's for sure. I mean, it's going to be a completely different. Yes, I mean, that's definitely for sure. Yeah, I totally believe that.
But just if you go lower in infratemporal cortex, then you find hundreds of thousands of neurons that will work.
Well, of course, yes. Yeah. Totally agree. And yeah, I mean, and what I think and what this community thinks is that these are projections from the infratemporal cortex. In other words, from the place where whole object learning happens. There are projections to the MTL, to the medial temporal lobe. Okay, this is what their current explanation is.
Yeah, I'll stop if it's not useful. But if you blow out the hippocampus and destroy that connection, then you can carry on conversations. You just can't learn anything.
Okay, right. Of course. Oh, yes.
Take the hippocampus
yes,
out.
I understand.
But so
yeah.
you have to be
Right.
In terms of having a hippocampus.
Right. Okay. Funny thing, I mean, these usually are called, assembly cells are called, memory cells are called Jennifer Aniston cells. Okay, so all right. So, we have a conjecture about hardware. We have our specs. We want to have an algorithm. How are assemblies formed, and how does association happen? Okay, so, and as I warned you at the beginning, so we like to prove things, and so we want to find a very simple model where you can prove that both learning of memories, stable memories can happen, and associations. Okay, so and now this is the infratemporal cortex, and this is the MTL. What we conjecture is that this thing fires repeatedly, and in response, an assembly emerges in the medial temporal lobe. Okay, and also that if two memories like Obama and Eiffel fire repeatedly together, then these corresponding assemblies are going to creep a little closer together and overlap. Okay, and these people were lucky to catch a cell in that overlap. Okay, that went from Eiffel only to Eiffel and Obama. Okay, and in fact, in simulations by Wolfgang's group, recurrent neural network model support the conjecture, right? I mean, but I told you we want to prove it. In fact, something else supports the conjecture. It's a story that Richard Axel wrote in a paper, in the discussion of the paper. And the story is the following. I mean, the story is about how Axel thinks that an assembly is formed in the piriform cortex of mouse, or an old structure that is connected to olfaction, in response to firing from the olfactory bulb for a particular odorant. And here is what his narrative is. An odorant may cause a small subset of neurons in the piriform cortex to fire. This small fraction of cells would then generate sufficient recurrent excitations to recruit a larger population of neurons. Inhibition triggered by this activity will prevent further firing, or will restrict firing. In the extreme, some cells could receive enough recurrent input to fire without receiving initial input. In other words, what Axel says, that there are some lucky cells that get a lot of projection from the olfactory bulb, but then they recruit new ones, and there is sort of a balance in the final assembly between born rich and newer recruits. Okay. I'll describe the mathematical model we used, and suppose that we have two large excitatory neurons, and this is the sensory cortex, let's say, and the memory area, or MTL. There are synapses that project from the sensory cortex to the MTL and recurrent connections, and they form a random GNP-directed graphs, like the graph I described before. We assume discrete time because we want a very simple model that we can prove something about. We say that the presentation of the stimulus is that a small set of sensory cortex neurons fire for a small number of steps. This is the Eiffel Tower assembly in the inferotemporal cortex firing. Okay, and then at each time t after that, a set A sub t of k memory area neurons in that have the largest synaptic input from either SC or recurrently from the memory area, fire. And now we are using sort of a very heavy assumption that we are selecting the k largest neurons. But we can also show that the same conclusion can be done if you have a inhibitory population that reacts faster. And we assume that synapses have a very simple rule of Hebbian plasticity, which basically says that the very simple thing that if at time t cell I fires and at time t plus 1 cell j fires, the weight of synapse ij increases by some amount. Okay.
So the randomness becomes less and less random by the.
Sorry?
The randomness becomes less and less random.
This is what randomized algorithms do. Yes, right. Yes.
You are. Less random.
Sorry?
The randomness is the initial.
The only randomness we have here is the randomness of the graph.
But that's the initial randomness, right? With plasticity that assumes.
Exactly. Yeah.
That
Yeah.
will change. Right?
Yeah. Of course. Yeah. Plasticity means that the way the graph stays the same all the time. The weights change, but that's important.
Yeah.
That's important.
Yeah. So
that's
the
important.
weights will change.
Right. Exactly. So, what you can prove? I'm not going to bother you with the result, but you can prove the precise narrative of assembly formation in Axel et al. Okay. And we also can prove that after the sequence of presentation, Eiffel, memory, Obama, memory, then Eiffel and Obama together, then Eiffel, then Obama, a small but not binding set of cells in the Eiffel assembly will also respond to Obama and vice versa. And of course, all of this with high probability. Okay. All right. So, stronger results you get if you assume a more a more elaborate model of connectivity, not just GMP, but something that we call GMP++, which is the following. That I told you, let's say that the chance that between two nodes, the chance that there is a directed edge this way is 1%. Now, condition on that, the chance that the reverse one, this is called reciprocity, and has been observed. In Song et al. 15 years ago, but also in many subsequent papers, experiments. Then the chance that there is an arrow going back is not 1%, but 10%, 5%, 6%, 10%. And also something that's called triangle completion, that given that these two synapses exist, then the chance that the triangle is completed is also very high. And it turns out that there is a reason why these give better results. And watch, the reason is the following, that if you take two cells in this assembly, in the memory, they look like random cells, right? From all points of view, except that they all are likely to have high connectivity with these guys, okay? And if you think about that, there is a birthday paradox, okay? There is a birthday paradox phenomenon which says that it's very likely that they have a common ancestor. And once you have that, then they're more likely to be they're much more likely to be connected. Okay, so this is sort of one thing that makes it work. Okay, so let me finish with two questions of many, and two things that I'm very curious about. I told you one. Are assemblies indeed more densely connected than random sets, than the memory area in general? Can combinatorial completion biases, such as reciprocity and triangle completion, be a crucial part of the way the brain works? I guess the trivial answer is yes, because otherwise they wouldn't be there. But I would like to understand what is how they are created and what is their use. Can a mechanism similar to the one described here be a part of the brain circuit for building syntax trees? Okay, so I don't know if you are following this, but there has been an explosion of evidence, of experimental evidence in the last maybe 2 years, suggesting. So if you read this, if I read this 6 months ago, I would ask the speaker, do you really believe that when we talk, we build trees in the left hemisphere? Okay, but now I'm inclined to believe it. Okay, so and my question is, I'll be delighted to give you.
What do you mean by syntax tree?
Sorry?
What do you mean by syntax tree?
Syntax trees are what linguists do in order to understand a sentence. Okay, and are explicit trees of degree 2, and there is growing evidence that something like that happens when we talk and when we hear language. Okay, there are suspects, areas implicated, and so on. But in Broca's area, for example, parts of Broca's area is where the internal nodes of these trees seem to be formed.
I see. So the puzzle is that one of the network is random, but building something not random.
Exactly. Yeah. Yeah, you said it right. So, to finish, we think algorithmically. We are mathematicians in heart. Okay, so we like proving theorems. We know about complexity and randomness, and we know about we don't know the cartoon complexity. We know the real meaning of complexity. Okay, and we like to explore interesting new areas and learn new tricks. And we look forward to interacting with you and learning from you. Thank you very much.
So in the last example that you gave, what is special about the Erdős-Rényi initialization of the graph? So why not? So what happens if you start with everything connected to everything?
Everything connected to everything.
Or just another random graph? What is special about it?
Okay, I like to work with friends, and random graphs are my friends. Okay, and I mean, I don't know how else to say it. Okay, so
Is there any special property that?
Yes, absolutely. The special property is called Bernoulli distribution and its tractability of its approximations. Okay. Sorry.
So is it more because it's easy to work with an Erdős-Rényi graph that you use it, or is it, do you have any reason to think that this is how?
Now you are searching into my soul. Okay.
So, how do you compare like the brain with the deep net? Do you think that deep nets are essentially the brain is a deep net, or deep nets can be stronger than brain even?
That's not as bad as consciousness, but it's almost okay. Yeah. So, all right, deep nets. Okay, there are brain scientists and deep net engineers and scientists know that there are huge differences. Okay. If you want to focus on one, is that the deep nets need equal synaptic weights going forward and backward. But there are more.
But is there like a possibility that one is stronger than the other one? Like for example, you can say the same thing.
They are both Turing machines.
In that sense, no.
I mean, Wolfgang told us that. I mean, yeah. Yes.
So when the algorithm finishes, when all the synaptic weights converge to whatever they're supposed to converge to, does any layer structure come out of the graph?
Out of the graph. So what we find very interesting that happens is that there is a stable assembly formed in the other one. So every time, some of these same neurons fire, this assembly will catch fire. Okay, so there is a permanent memory. We know that nothing is permanent and so on, but this is formed. And also we know that nothing in the brain will be, it will be much more chaotic, noisy, wet, and so on. So but this is like an existence theorem. Okay, so that there is a way. The same with the simulations, the results in Wolfgang's group, right? There is a way. So for this to happen, okay, and who knows what happens in reality? So but maybe something like this, a very distant approximation of this may be happening.
Okay, Christos, thanks very much.
Thank you.
We'll resume at 1:30 with Sam.